We are discussing Newton's law of gravity here. In this brief little discussion हम लोग Newton's law of gravity discuss करने वाले हैं. तो in Newton's law of gravity we are looking at the force of attraction between any two masses in the universe. Now how Newton arrived at it is an interesting little story. Now what happened was that Newton compared the acceleration of an apple falling from a tree to the acceleration of the moon. Now how he did all that, we will have a brief little discussion on this. Of course no apple fell on his head, I'm sure that is just a legend. So what happened was that he knew that if an apple falls near the surface of the earth, then it accelerates towards the center of the earth with an acceleration that equals 9.8 meter per second square. Now this figure 9.8 meter per second square was very well known in Newton's time. This had been measured by Galileo much before Newton did. So this was already known, this was very well understood in Newton's time. G was known, R was known. Now the other thing that Newton did was he compared the acceleration of the moon to the apple. Now how he came up with the acceleration of the moon, in Newton's time it was very well known that the radius of the orbit of the moon around the earth is about 60 times the radius r of the earth. We've shown the radius r of the earth here. Now the radius of the orbit of the moon is approximately 60 times the radius of the earth. This was known. Also known in Newton's time was the fact that the time period of revolution of the moon around the earth is 27.3 days. So these two bits of information were available to Newton, and what did he do with it? Now the acceleration of the apple is already known. Let's see what's the acceleration of the moon. Now the moon is moving in a circular orbit around the earth, so its acceleration will be omega square times the radius r of the orbit. Now omega is 2 pi by time period, so we know the time period of the moon, we can convert that to seconds. So 2 pi by t whole squared gives us omega square times the radius of the orbit of the moon, which is 60 r. Now when he calculated this acceleration, it came out to approximately 9.8 divided by 60 square. Now this acceleration of the orbit, this acceleration of the moon comes out to be 9.8 divided by 60 square. That means the acceleration of the moon is 1 by 60 square times the acceleration of the apple. Now Newton therefore came up with a little hunch, a little hypothesis. And the hypothesis is that the earth attracts objects towards its center with a force which varies inversely with the square of the distance of that object from the center of the earth. So this is the force which causes whatever acceleration the object undergoes, and therefore he applied this little hunch, this hypothesis, to the acceleration of apple and the moon. Now the acceleration of the apple towards the center of the earth is therefore inversely proportional to square of the distance r square from the square of the distance r from the center of the earth. Acceleration of the moon will therefore be proportional to 1 by 60 r whole squared. Why 60 r? Because the orbit of the moon is 60 times the radius of the earth. So for the moon it's 1 by 60 r whole squared. Now you divide this equation 1 we have here with equation 2, and we get the ratio of the acceleration of the apple to the acceleration of the moon, and we end up with 60 square here, and therefore finally Newton arrives at a conclusion which is correctly matching his observation of nature. He observed nature and came up with the idea that the moon accelerates towards the center of the earth. Now he came to a conclusion here that the moon accelerates towards the center of the earth with an acceleration which is 1 by 60 square times the acceleration of the apple. That was his observation of nature, and his hypothesis that the acceleration is inversely proportional to square of distance gave him the same result. And so he moved on further. Now he knows that the acceleration of the apple towards the center of the earth is proportional inversely to square of this distance r, right? So this acceleration g of the apple is proportional to 1 by r square. Now the force therefore must be acceleration times the mass of the apple. So the gravitational force on the apple is m into 1 by r square, right? Now the force on the apple depends on the mass of the apple, but then he also knew his own third law. Who else would know it better, of course? So the force that the earth applies on the apple is reciprocated by the apple by a force on the earth which is equal and opposite. So if the force on the apple depends on the mass of the apple, then the force on the earth on a reciprocal basis should depend on the mass of the earth. So the force of gravity between the moon and the earth, or the apple and the earth, we're talking apple and earth here. So the force of gravity between apple and earth depends not only on the mass of the apple but also on the mass of the earth. So force of gravity between the apple and the earth is proportional to product of the masses of the apple and the earth, and inversely proportional to the square of the distance r between them. This was his conclusion about the apple and the earth. And from here he extrapolated to all pairs of masses. So if you have two masses m1 and m2 separated by a distance r, the assumption is that the force of gravity will be directly proportional to the product of the masses and inversely to the square of the distance between them. And this brings us to what is called Newton's law of gravity. What this says is that if we have any two masses anywhere in the universe having masses m1 and m2 separated by a distance r, then they will attract each other by a force of gravity which will be along the line joining them, and it will be proportional to the product of the masses, inversely proportional to the square of the distance between them. There is of course a constant of proportionality which we know as Newton's or the universal gravitational constant. The value of this gravitational constant is very well known to be 6.67 into 10 to the power minus 11 Newton meter square per kg square. However, Newton did not know this. This was calculated in an experiment by Henry Cavendish approximately about 80-90 years after Newton's publication of the Principia. So this then is your introduction to Newton's law of gravity. More on this in the upcoming videos.